All right, people at home, we're going to talk about the gas laws. We're going to talk about a temperature scale. All of these lessons are covered in the Ed puzzles that you've been assigned. And basically, if you want to watch this video, great. You'll get information delivered to you in the same way that the kids in class are getting it delivered. So I'm just going to make this video. I'm going to post it. I'm just going to let it run, and then you can watch it if you like. All right, first things first. This next area is going to be on the gas laws, okay? This next little section of chemistry, okay? And we know what gases are. Gases are like when we have molecules, and they're not connected to each other at all, right? And gas particles just float off in any direction until they bounce into another gas particle, maybe, and bounce off of it. Or if they're in a container, maybe a gas molecule will just bounce off the edge of the container. But gas molecules aren't liquids or solids. They don't stick to each other. They just move around, right? Okay. Now, before we do any math, and there's very simple math with the gas laws, but before we do any math, we need to understand that we have to use this new temperature scale called Kelvin. Have you all heard of Kelvin before? Have we talked about it in class? I don't remember. We have? Okay. Kelvin. Kelvin temperature grades are the same size as Celsius, okay? And that's on purpose. What I mean is, if you're in the room and it got 10 degrees hotter Kelvin, then it also got 10 degrees hotter Celsius. They're not different sizes. Like Celsius and Fahrenheit, the units are different sizes. Fahrenheit units are much smaller. Does that make sense? Like if it got 30 degrees hotter in Celsius, then that means it got like 82 degrees hotter in Fahrenheit, because the Fahrenheit units are smaller. But Celsius, Kelvin and Celsius, their units are the same size, but they are assigned different numbers. And the whole thing is based on water with Celsius, right? So what we call 0 and 0 degrees Celsius, that's when water freezes, right? And what we call 0 in Kelvin, that is absolute 0. Now those are two very different things, all right? At 0 degrees Celsius, water turns from a liquid to a solid. At absolute 0, or 0 degrees Kelvin, all the physics in the universe break down. So these are two different things, all right? At absolute 0, it means that gas particles, atoms, molecules, even theoretically electrons, have stopped all motion. At 0 degrees Celsius, it means that water is frozen. You can just wear a jacket here, right? Here you died way before we even got close to this. And not only did you die, but your body turned to a solid, and then it became so brittle it just fell apart, and then there's no existence of you or anything, nothing, dead, done, 0 degrees, absolute 0. Okay. Now, the units are the same size, so if you go backwards on the Celsius scale, and you get to negative 273 degrees, that's the same thing as 0 degrees Kelvin. All right? So if you go this way on the Kelvin scale, then 273 degrees Kelvin, that's equal to 0 degrees Celsius. So 100 degrees Celsius, that's when water boils, right? So at what temperature Kelvin would water boil? 373. See, you just add 273 to this. All the units are the same size. Does that make sense? Now we have to use the Kelvin scale to do our gas law problems. And here's the reason why. Let's say we did a problem. And there's a really simple problem here. Let's see. Charles's law says that if you have a balloon and you know its temperature and its volume, and then you take this balloon and you make it twice as hot, then the volume will get twice as big. Okay? Right? Well, what if you had a balloon? Let's say you had a balloon and it was like, I don't know, at 30 degrees Celsius. And for some reason you stupidly used Celsius in your equation. And then it went down to negative 10 degrees Celsius. Then if you knew the first volume, the next volume you came up with would have a negative answer. Is there any way to have a negative volume? Can you have an object and it gets smaller and smaller and smaller and smaller and smaller, and then it gets down to nothing, and then somehow it gets smaller than small? No, so you can't ever use Celsius, because you could end up with negative volumes, and that would just be garbage, right? So instead of using 30 degrees Celsius and negative 10 degrees Celsius, you would use 303 degrees Kelvin and 263 degrees Kelvin. And then that will give you the correct answer. In other words, Celsius plus 273, that's equal to your Kelvin. And if this blew by you, don't worry, you're going to see it in the ed puzzle in just a minute. Okay? So, the gas laws are pretty much common sense in a way. All right? And let's try something here. I'm just off the cuff here. How about, let me see my history. I think I've got a good video I want to show you. All right, this guy right here, they are, hang on, we'll give it a second. The projector timed itself off. All right. The first thing that we need to understand is common sense. One time this is a true story. One time I went to the grocery store, okay, at Food Line. This is a long time ago when I first moved here. In Food Line, they used to give away balloons to the kids. When you went to the grocery store with your mom and you went through the line, they would blow you up a balloon and hand it to you. A kid, you'd be stoked, man. You're getting out of there with a balloon, right? Well, one time I'm walking into the grocery store, and it's hot. It's like July, it's summertime, and a little kid comes walking out of the grocery store with his mom. And he's like, doo-doo-doo, gets about 10 steps outside, and boom! The balloon exploded. And he started crying, and the mom turned around and drug him back inside. And the manager, I went through and I shopped, and I came by, and the manager was talking to the teenager who filled the balloons up. And he said, I told you, you can't fill the balloons up all the way because they're going to bust when the kids take them outside. Now, why do you think the balloon busted when the kid took it outside? What? Yeah, the balloon tried to get bigger because it got hotter and it exploded, right? Because the balloon couldn't take the new pressure. All right, so check this out. And what's happening here? They're filling up a hot air balloon, right? And at first, there's just a big fan, right? And they just try to blow a bunch of air in there and get the balloon to swell up. So they're just adding more air inside the balloon than what's outside the balloon. They're creating more pressure, right? And then eventually, you heat that air up, right? And the balloon tries to swell up even more, and then it becomes less dense than the air around it, and the balloon will stand up. So all we're doing, is making the balloon stretch. We're increasing the temperature inside of the balloon. We're making it stretch, and it's getting bigger. The volume's increasing. And then it's less dense than the air around it. And there you go. And then when you're taking your balloon and you're flying around, as long as you control the temperature of the balloon, you can control how high you're going to float. Does that make sense? All right, so that's how hot air balloons work. So a lot of this stuff is kind of intuitive to you. So I'm going to go through some of these laws real quick. All right? And when I say real quick, I mean very sincerely, I'm going to go pretty quickly. This guy, Charles, he was one of the first inventors of the hot air balloon. And this is his very simple equation. It seems simple to us now, but he really had to do some math to figure this out. But as long as you're using Kelvin, if you know the initial volume of a closed balloon, okay, not just like the hot air balloon, but a balloon that's closed, right? Or a container that's closed, that's flexible. If you know the original volume and the original temperature, then if you change the temperature, you know exactly how big it's going to get. This is called Charles's Law, and it's very simple, all right? This is why the balloon exploded, okay? Now, another guy, at the same time, came up with this law. And it's also pretty intuitive. This is called Boyle's Law. Now, this is when we're not changing the temperature, right? There's no temperature change here. And it says, if you know the pressure and the volume of the original balloon, then if you change the pressure, you know the new volume. Does that make sense? So what if you had a balloon and you let it float up into the atmosphere and it got less and less pressure on it? What's going to happen to the balloon? Yeah, it's going to get bigger and bigger until it pops. Does that make sense? How about this? What if you had a balloon, and maybe you didn't fill it up all the way. It's a birthday balloon, right? But it's a little bit squishy. And then you take it, in your birthday's in the summer, and you swim down deep in the pool where the pressure is greater. What's going to happen to the size of the balloon? As you go deeper underwater, it's going to shrink. This is Boyle's Law. If you increase the pressure on the balloon's got to shrink, right? That's it. Or, what if you had a balloon in your hand and then you decrease the volume? What happens to the balloon? Does it feel harder or softer? If you squeeze the balloon, it's going to feel harder. If you make the volume smaller, then the pressure's got to go up. So in other words, as pressure goes up, volume goes down, or as volume goes up, pressure goes down. That's it. This is Boyle's Law. So, what if I did this? This is also a very common sense law. This is called Gay-Lussac's Law, because those are two different scientists' names that worked on it. And they said, here, you only have pressure and temperature, pressure and temperature. What if you had a pot, okay? But you screwed the lid onto it. So the lid is now tight. And the pot cannot change size. See how there's no volume here in this? So the volume of this pot can't change. And then you put it on the stove. And you tell people, hey, this can cook things instantly. And you get it, it's an instant pot. You seen the instant pots? Okay. Anyway, that's literally what it is. You screw the lid on. Now, as it gets hotter in there, the pressure's going to go up. Right? Or, as the pressure goes up, it's also going to get hotter in there. Does that make sense? So, when you cook with an Instant Pot or a pressure cooker, it's way, way hotter inside. Because as the pressure goes up, the temperature can also go up. In a regular pot, the lid just wobbles, and the pressure never changes. Does that make sense? So, this is Gay-Lussac's Law. If you can keep a lid on this thing, as you increase the temperature, you'll also increase the pressure. Does that make sense? So if we take all three of those laws together, then we have this very simple Algebra 1 formula. And this is called the combined gas law. Combined gas law. Because it's a combination of, ready? It's a combination of Charles's law, Boyle's law, and Gay-Lussac's law. All of them together. So you can be given formulas, and someone could give you 5 of the variables, and then you can solve for the other one using Algebra 1. Does that make sense? And basically, that's all there is to it. Now, let's do one, just for the heck of it. You guys can watch me. I'll write it up here. All right? We'll talk about what happens to a balloon in this one. All right? I'm going to leave this right here on the board. See, a balloon at 1 atmosphere, and this is a measurement of pressure that you'll learn on an ed puzzle, and 300 degrees Kelvin, that's just a little bit hotter than it is in the room, okay? A balloon at 1 atmosphere and 300 degrees Kelvin has a volume of 20 liters, all right? If the temperature drops to 290 degrees Kelvin and the pressure stays the same, what is the new volume of the balloon? Question mark. So that's really simple. Watch what I'm going to do here. Here's how you get all the problems right on your worksheet that you'll eventually see. Here's how you get them all right. You write this formula down every time. And then you read the question and put the number where those letters go. That's as simple as I can make it. If you can do Algebra 1, and I mean that sincerely, that's not me like being snotty. If you can do Algebra 1, then you can do this. Watch, ready? A balloon at 1 atmosphere. So in the beginning, the first pressure is 1 atmosphere, 1 ATM. And 300 degrees Kelvin, is that the volume or the temperature? It's the temperature. So the first temperature is 300 degrees Kelvin. Has a volume of 20 liters. So the first volume is 20 liters. So we have 1 times 20 over 300 equals, now the 2's here mean later, right? All right? If the temperature drops to 290, so the new temperature is 290, and the pressure stays the same, so we can just put a 1 here again, right? Right? Or we could just erase both of these numbers. Okay? What is the new volume? So we're solving for V2. Does that make sense? So very simply, how do you solve for V2? We need to leave it by itself. When the number's on the bottom, on this side, you move it to the opposite side. What's the opposite of divided by 290? So if it's on the bottom on this side, you put times up here. Does that make sense? If it's on the top on this side, then you put it times down here. That's very simple. If it's on the top on one side, move it to the bottom on the other. If it's on the bottom, move it to the top. Algebra 1, right? So then our answer would be 290 times 1 times 20 over 1 times 300. So we take our calculator, and I'll say 290 times 1 times 20 divided by, and then I'm going to hit this parentheses here, parentheses, 1 times 300, close the parentheses, equals. The new volume is going to be 19.3. And you can ask yourself, 19.3 liters. You can ask yourself, does that make sense? Do you think if the balloon got colder, it would get a little bit smaller? Yeah, it would. Last thing on this video for you people at home is this. When we talk about pressure, when I talk to you about pressure, there are 3 or 4 different units I can use for pressure with you, okay? And those units are found on your tables on page 1. So if you look at the top of page 1 on your tables, it says standard pressure, and that means like the pressure at sea level, okay? You could call that pressure at sea level, you could call it 1 atmosphere, or if you wanted to use different units, you could call it 101.3 kilopascals, or you could call it 760 millimeters of mercury, or torrents, which are the same thing. Now these are 3 different ways that pressure's been measured in the past, but they all mean the exact same amount of pressure. Basically, the pressure in this room is 1 atmosphere, or 101.3 kilopascals, or 760 millimeters of mercury, okay? You've heard millimeters of mercury said on the news a bunch when they talk about the weather. If you're into cars, you can look on your tires, and they'll give you different pressure measurements. You have PSI, or kilograms per meter squared. All right? Some tires, I'm sure somewhere, have kilopascals written on them. All right? So these are just different units of pressure. All 3 of these are the same thing. So don't get nervous if you go, oh, what's a kilopascal? Put that number for pressure. Does that make sense? That's it. So people at home, get on those ed puzzles, people at home.